You've seen the incredible images AI can create these days, right? Photorealistic portraits, mind-bending landscapes. It really feels like magic. We can type a few words and create basically anything we can imagine.
But what if I told you that underneath the hood of all this futuristic tech, many of our most advanced AI models are running on an old, clunky, and just plain inefficient engine? Yeah, there's a hidden bottleneck that's been holding back the true potential of AI art for years. All right, let's get into it. The problem isn't with the big, powerful diffusion models you've probably heard about. Nope. It's in a much smaller, often overlooked component that works right alongside them, something called the autoencoder. You can think of it as the universal translator for the AI. It's the thing that turns a regular image into a special language the AI can actually understand and work with.
So picture an autoencoder, like a super advanced photocopier. First, it takes a beautiful high-res image and shrinks it down into a really compact code. That's its latent space. Then, a second part of the machine tries to perfectly rebuild the original image using only that tiny piece of code. Now, the quality of that compressed code, it is absolutely crucial for everything the AI does next.
And here's the kicker. For years, pretty much all the top-tier AI image models, from the original Stable Diffusion all the way to the newer diffusion transformers, they've all been using the exact same autoencoder. It's called the SDVAE from the first Stable Diffusion model. It was a huge deal when it came out, but now, well, now it's the weakest link in the entire chain.
So, what's so bad about this old engine? Well, researchers have pinpointed some really fundamental problems with it. And it's not just slowing things down, it's actively limiting the quality and creativity of the images we can generate. It really comes down to three key flaws. First, its architecture is just old. It's inefficient. Second, that compressed code it creates is way too small. It's like trying to describe the Mona Lisa using only 10 words. You're going to lose a lot of important detail. But the biggest problem by far is the third one. It's only trained to reconstruct pixels. It learns to copy what an image looks like, but it has zero real understanding of what is in the image. It sees a pattern of colors, not a dog or a house. And check this out. This slide really shows the raw inefficiency. Just look at the G-flops, which is basically a measure of how much computer power you need. The old SDVAE is a total gas guzzler. It needs about 6 times more power for its encoder and 3 times more for its decoder, compared to the new approach we're about to talk about. It's just burning energy for no reason.
So this brings us to the solution. Instead of trying to tune up that old rusty engine, these researchers decided to just replace it entirely with something way, way smarter. They call it a Representation Autoencoder, or RAE for short. And the whole philosophy behind it is completely different. The old VAE, it learned from scratch with one single goal: copy the pixels perfectly. But in RAE, it does something genius. It takes a powerful, pre-trained vision model, like Meta's Dino V2, an AI that already understands concepts from being trained on tons of images, and it uses that as its expert encoder. It's the difference between learning to trace a drawing versus having an expert artist describe the scene to you.
And the results? Whoa, look at this. This chart basically measures how well that compressed code actually understands the content of an image. The old VAE scores a measly 8%. The new RAE, because it's using that expert Dino V2 model, scores a staggering 84.5%. It's not even in the same league. It's a completely different sport. Okay, so if the RAEA is so much better, why didn't somebody do this ages ago? Well, it turns out that its special code was so much richer and more detailed. Remember, it's the encyclopedia, not the 10-word description, that the existing diffusion models had no idea how to handle it. They were built for the simple stuff, not this fire hose of information. And that was the huge puzzle the researchers had to crack. How do you tame this powerful new beast? You see, if you just took a standard diffusion transformer and plugged in these new, much better latents, it just didn't work. In fact, it actually performed way, way worse. But they figured it out with 3 key breakthroughs. First, since the RAE's code was so much richer, they had to widen the pipe of the main diffusion model to let all that information flow through. Simple enough. Second, they had to tweak the whole denoising process, which is how these models learn, to work properly with this much richer code. And finally, they basically toughened up the decoder, training it to create a perfect image even if the instructions it got from the main model weren't 100% perfect. So,
With those core problems solved, the system was finally working. But these researchers didn't stop there. Oh no. To really push this thing to the absolute limit, they added one final, brilliant innovation that basically acts like a supercharger on top of this already new engine. They call it a DTDH. You can think of it as a shallow but very wide specialist module that sits right on top of the main model. Its only job is denoising. So by giving that one important task to a specialized, super wide part, they can handle that rich RAE code way more efficiently. They get all the benefits of the new engine without making the whole thing slow and expensive to run.
And the results are just phenomenal. This chart shows how much faster their new approach gets to a high-quality result during training. Compared to a standard model using the old VAE, it's up to 47 times faster. Even when you put it up against other recent optimized methods, it's still 16 times faster. This isn't just an improvement, it's a monumental leap in training efficiency.
So, you have a much smarter autoencoder, some clever training adjustments, and a supercharged architecture. What does that all add up to? What kind of performance did they actually get? Well, they didn't just improve efficiency. They went and set a new gold standard for image quality.
This is the number that matters, 1.13. This is the new state-of-the-art FID score on the big ImageNet benchmark. It's a measure of image quality, where lower is better. And just so you know, the community fights tooth and nail just to shave off a few hundredths of a point. This is a huge jump.
And here's that number in context. You can just see the march of progress. All these previous state-of-the-art models, all of them built on that old VAE. The best anyone had ever gotten was a 1.15. This new DITDH model, built on that new RAE foundation, just unequivocally beats them all. It sets a new best-in-class performance. You know, the researchers themselves say it best in their paper. They conclude that this new approach, quote, offers clear advantages and should be the new default for diffusion transformer training. This really is a paradigm shift. So the big takeaway here is this. We're seeing a fundamental shift away from AI models that just learn to copy pixels and toward models that generate images from a true, deep understanding of what's in them. It's changing the very foundation of AI image generation, and it leaves us with one really exciting question. What are we going to create when AI learns to generate images not from pixels, but from meaning?